Today we're going to finish up the probability chapter, chapter 6. This is our third day. We're going to get some more rules, kind of finish up as far as the rules go and try to get in some examples of types of questions you might see. So let's start with some definitions, and you've probably had these before, maybe even in class on some problems, but union and intersection. So those are two terms you need to know. First of all, union is the U shape, intersection is the upside down shape. Union means or, and intersection means and. Okay, so I remember that because the upside down one looks like a lowercase n, and sounds like in, especially when you say it in conversation. So here's a couple of examples. Let's say these are all of my AP Stat students. And I'm going to draw a little Venn diagram. This section's going to have a lot of Venn diagrams in it. I'm going to have a bubble for MSTC. We have a lot of MSTC students in this class, and I'm going to have a bubble for the gals. Okay, so this overall sample space is all of my AP Stat students. I have a bubble for gals, a bubble for MSTC, and there's some overlap in those two groups because obviously we do have girls who are in MSTC. Let's say that my percentages are, let's say, 20%, and let's call this 0.3 girls, 0.6. I'm not sure how close that is to reality, but we'll go along with that. So here's a Venn diagram set up. If I ask you for the probability of MSTC union gals, or what proportion of them are both, or are union, not both, that's or, that's going to be 80% because everybody except 20% are in one of those bubbles, or both. All right, technically I have 50% girls and 50% MSTC, but I can't just add those together. I have to subtract the overlap, which is a concept we've discussed some. If I change it up, MSTC intersect gals, or and, that's going to be the 0.2. 20% are part of both bubbles, and that's that overlap in the middle. All right, so those symbols you need to know what union and intersection mean. I personally would rather say and or, just as simpler. But you never know the wording, especially on the AP exam, so we're going to need to know those symbols and those words as well. Okay, I think I've talked about this one as well. There's a rule in the book called the addition rule for disjoint events. That just means, if you're going to figure out, if you have events that are not overlapping, and you want to figure out the probability that one or more happens, that more than one, just add those separate probabilities together. Okay, if I have, let's call this disjoint events. So if I want to know the probability of A or B or C, then all I have to do is add them together. No overlap. And that one just kind of makes sense. If there's nothing to subtract, there's no overlap, then you just don't subtract it. But they're getting all these rules out officially in these sections. Okay, so in general, you can say this. This is called the general addition rule. Basically what it says is the same thing. It says the probability of A or B is equal to the probability of A plus the probability of B minus probability of A intersect B. And really this rule could stand on its own because if they're disjoint, then the probability of A intersect B or A and B is 0 anyway. So it would just be negligible and you would just be adding them. So this really, just use your common sense. If you've got an overlap, Don't add it up. Don't include both parts, or include it and then subtract the overlap. All right, so these rules are a lot more complicated written than they are in just common sense. All right, so now let's talk about conditional. We've done some of this already. The given questions. What's the probability that it's a king given it's a heart? It's a face card given it's, that sort of thing. But let's get an official definition of conditional probability, or A given B. Probability of, let me start with this one. The addition rule above just kind of is a one rule for all. If A intersect B happens to be 0, then it goes away anyway. So that's the only rule we need. This is the only rule we need for A and B. The probability of A and B is the probability of A times the probability of B, given that A has already happened. If these events A and B are independent, then the probability of B given A is the same as just B in general. So what we've written in the past is just the probability of A times the probability of B, because these two things are the same if it's independent. So again, you can just have this be your one go-to rule, kind of the way this one was, because if they're independent, then B is just whatever it was, without having to worry about whether A happened or not. So that's our general multiplication rule that always works. So here is our definition of conditional probability. And this one comes up quite a bit in the problems that we'll be doing. And again, it just kind of puts a more mathematical spin on what we do with common sense. Probability of B given A is equal to probability of A and B divided by the probability of A. If we want to test out that formula, we can look at an example that we already know how to do, a conditional that we know how to do with a two-way table. So look at this example. Here's a two-way table coming up. The question is, what's the probability of the person being a female? This is male, female, A, B, C. Those could be grades or whatever groups, just a quick example. What's the probability of female given B? So according to our formula, well, first just by common sense and the way we've done it before, female given B means only look at the B's and now pick the probability of being a female, which is 5 out of 20. So if they were all that easy, it would be nice, but sometimes this formula will be necessary. So let's look at it with the formula. According to the formula, female given B should be female and B over B. All I did was substitute in F and B for A and B in our formula. All right, so female and B. Now that's not a given, so that's 5 out of 50. 5 out of 50 people are both female and B. And the probability of B is 20 out of 50. All right, so those numbers we can just get from the table. If you put those together in the formula, here's what you get. 5 out of 50 on top, 20 out of 50 on the bottom. Dividing by 20 out of 50 is the same as multiplying by 50 over 20. And we cancel. And we see 5 out of 20, which we already knew to be the answer anyway, which is 1/4. So like I said, you're not going to actually use this formula if you're given a two-way table, because the info is all right out in front of you. But this formula is important, and I just wanted to confirm for you that it actually worked out. And that same type of question could be asked about a Venn diagram. I'm just going to skip back and add one in. So just maybe add this to the margins of your paper where your Venn diagram is. What about a question like, what's the probability of gal given MSTC? Okay, just to practice the formula again, this would be the probability of gal and MSTC over the probability of MSTC. And hopefully it'll make sense. You know, I can kind of get this answer just by the given info. Gal given MSTC. Given MSTC, I'm talking about 50% of the people, 0.5 if you add up both of these numbers. And gal given that is 0.2 over 0.5 because 0.2 is the amount of gals who are also MSTC. 0.2 out of 0.5. So that's 40% probability. All right, the formula is going to work, and it'll be given in scenarios where it's not that easy to tell. Okay, so the last thing I want to talk about is tree diagrams. I'm going to pause for a second and get a scenario set up. Keep this video time down, and you can copy it, and then we'll talk about it. Okay, so here's the scenario. Pause for a minute and copy it down if you need to. Sometimes you get a bunch of info thrown at you with a bunch of percentages, and you just need a way to organize it. If you're going to answer some probability questions, like right now, if I said, hey, read this, what's the probability that one of my golf team members makes it as a pro? Well, there's a lot to organize. A tree diagram is just an organization tool. So what we have here is a breakdown of all high school golfers. All right, they're in three categories mainly. We have the ones that go to college to play golf, the ones that go to college but not to play golf, and the ones that don't go to college at all. And each one of them has a chance of becoming a professional golfer. And these are all just made up, but we'll see if these were true, what my probabilities look like. Okay, so first of all, everybody who plays high school golf is going to go down one of three paths. Either they play in college, they go but they are not part of the golf team there, or they don't go to college at all. And then from each of these branches, we have two possibilities. We have either pro or not. Right, and that's going to be the same because that's what we're talking about, pro or not. And there's lots of variables that we could measure, but we're talking about, do these people make it as a professional golfer or not? So now we just go back in and we fill in our percentages. But we're going to put them in decimal form because when we multiply, we need to be multiplying in decimal form. Okay, so just put next to it the likelihood that it happens. 20, 68, and 12 are the probabilities of playing in college, not playing in college, and not going to college at all. Let's say, what was our number here? 10% of college golfers go pro, which means that 90% don't go pro. Every time you have a fork in the road, the different forks have to add up to 100% every single time. Right? Those that went to college but didn't play golf, I think I gave them, what, a 5% chance? Maybe they were just practicing. All right, make sure you don't do 0.5, 0.05, which means 0.95, 95% of them do not. And then 10% of these guys, 0.1 versus 0.9, they just go straight to the pros. Maybe they were so good they didn't even need to play in college, like LeBron or Jordan Spieth. Some of you know who that is. So anyway, if I want to know what's the probability that you went pro, there's 6 things that can happen here. You go to college and play, and you go pro. Right? That's 0.2 times 0.1. You go to college and you don't make it pro. You play in college and don't make it pro. All right, that's 2 outcomes. You go to college but don't play, and then you make it pro. Multiplying out as we go. You go to college and don't play and don't make it to the pros. Or you don't go to college at all, you still make it, and you still make the pros. Or you don't go to college at all, and you don't. All right, so these outcomes are not all equally likely. they are different based on the different chances. So if I want to know what's the probability that a high school golfer makes it to the pros, I add up all the ones that make that happen. So .02 is my top one. College but didn't play and then go pro, let's see, that I believe is .034. Let's see, that 10% of 68% would be 6.8, half of that's 3.4, and then .012 down here. Those are the three branches of the tree that ended up with the professional golfer. Let's see, those add up to 0.54066, I think. So there's a 6.6% chance that a high school golfer makes it. So you can see the tree diagram, what it's for. You've probably done tree diagrams of something before, and it just organizes our thoughts. And we'll have some better questions that are a little more challenging tree diagram questions that we'll do in class. All right, so that'll do it for probability day 3. Young out.